Good morning, everyone. Today we are going to continue our talk about corrosion and degradation of materials. So this is our second time. And last time I talked about electromotive the force EMF series when compared with the platinum. And so you should know that what is anodic and what is cathodic. Today's objective is to learn how to predict corrosion rate. And so we know the standard EMF series or the standard electrode, the potential EMF series, the metal, and as I told you guys, this is metal. This is cathodic. Cathodic means that they capture the free electrons, and anodic means that they give up the electrons, and so by giving up electrons, the metal atoms can become ions and then dissolve in the solution. So this is can result in the corrosion. So on the contrary, for these cathodic materials, because they capture the free electrons, and so they usually they can just use the free electrons and then combine. Then this is their ions. When their ions capture these free electrons, they become the atoms. So usually this is more cathodic materials, and they result in reduction. Reduction means that deposition. You can see more atoms on their electrode. So this is very, very important here. So metal with smaller standard electrode potential or standard EMF values, and they corrodes. For example, this is a CdNi, and Cd is a cadmium, is a toxic material. Ni is a nickel, and so Cd has lower standard electrode potential. As a result, when we connect these two guys together, and we will have so this is a cadmium will corrode, and nickel will experience the reduction action. So you can see cadmium. So here you can see we can have this corrosion. So on the nickel surface we can have this deposition. So prediction of corrosion rates, and how can we predict the corrosion rates? This is very, very important. If we can predict the corrosion rates, we can do something and to make these corrosion rates smaller and smaller. Maybe you can make it zero if it's possible, and so we can just eliminate the corrosion. That is the ideal case, but usually it's very, very difficult to achieve this. And here, so this is a zirconium, okay? I'm sorry, this is zinc, this is zinc. So this is a PT, platinum. So this is a Zn, because when compared with the PT platinum, and Zn has lower standard electrode potential. As a result, when we connect these two guys together, so Zn will give up electrons, and so these free electrons will be transmitted from zinc and to this PT. So the PT here, okay, so PT in this PT electrode, and the free electrons and will be given to this is hydrogen ions. So hydrogen ion, and they will become hydrogen atom. Two hydrogen atoms will become hydrogen. This is a molecule, and then will release as a gas. And so here, so this one is I think you can see here, and we have this is a corrosion here. The potential of the two electrodes will not be at the value from table 70.1 because the system is now a non-equilibrium one, right? So non-equilibrium one, because you connect them. So polarization. Polarization means that this is from one extreme to another extreme, two extremes. The displacement of each electrode potential from its equilibrium value. The displacement of each electrode potential from its equilibrium value. The polarization, the over voltage, the magnitude of this displacement. And you should know these two concepts. One is a polarization, one is over voltage. Any questions regarding this slide? So then, this activation polarization, so the condition wherein the reaction rate is controlled by the one step in the series that occurs at the slowest rate. And so you can see here, we have 4 steps here. First, adsorption of hydrogen ions from the solution onto the zinc surface. This is Zn, zinc. So electron transfer from zinc to form a hydrogen atom, right? So this hydrogen atom. So combining of 2 hydrogen atoms to form a molecule of hydrogen. This is what I told you. The covalence of many hydrogen molecules to form a bubble. So you can see here schematic representation of possible steps in the hydrogen reduction reaction, the rate of which is controlled by activation polarization. So this is zinc. So this is the hydrogen. This is zinc. This is the hydrogen ions. So these free electrons will be given to these hydrogen ions, and they become hydrogen atoms. And hydrogen atoms, they can form the molecules. Multiple hydrogen molecules will become a bubble. Any questions so far? For activation polarization, the relationship between over voltage, the eta A, and the current density I, the current, okay, electrical current, and can be described using this equation. So this is the over voltage eta A and the current density I. So this is the logarithmic. This is the natural. This is this log here. So this is the common log here. So this is logarithmic. You can see this logarithmic scale, the current density. So this is over voltage, the eta A. The voltage unit is voltage. So here, so at this point, next, so at this point, so this equilibrium. So here H2, so this is they give up the free electrons to the surrounding air environment. So this is called corrosion. So if this guy captures free electrons and become atoms and then molecules, so this guy is called reduction, right? So still remember reduction reaction and oxidation reaction. So this is the form a hydrogen electrode plot of activation polarization over voltage versus logarithm of the current density for both oxidation and reduction reactions. So this equation describes the relationship between eta A and 2 this is I, the current density. So concentration polarization. So this is when the reaction rate is limited by diffusion in the solution. In the solution here, you can see this is a cathode. So this is a cathode, okay? And this cathode, these hydrogen ions, So here is the depletion zone, and this is used up, a depletion zone. For hydrogen reduction, schematic representation of hydrogen ion distribution in the vicinity of the cathode. So low reaction rate, so this one low reaction rate and high concentration. For here, high reaction rate, you can see depletion zone. So this is hydrogen atoms, hydrogen ions, and they change to hydrogen atoms very quickly. This is a high reaction rates or low concentration wherein a depletion zone is formed. That gives rise to concentration polarization. This is called concentration polarization. Questions so far? And then this prediction of corrosion rates here. So this is over voltage. So this is over the voltage eta to positive, negative. This is 0 here. And so log current density I. And so here, so this is for this one. So okay, for this one is concentration polarization. And so this is second one is combined activation concentration polarization. So this is activation polarization and this is concentration polarization. So here, so this picture shows electrode kinetic behavior of zinc in acid solution on both oxidation, and so this is the reduction, and this is oxidation. So this is oxidation also. So this is reduction, and are rate limited by activation polarization. Activation polarization. And this is a VC. Okay, so this is a VC here. So this one shows schematic electrode kinetic behavior for metal ion. And the reduction reaction is under combined activation concentration polarization control. So this is activation polarization. So this is the concentration polarization.